Let's start the session for real. If everyone can mute themselves, or if Luke can mute everybody, but
yeah, let me try muting everybody. I may have to individually unmute all of you.
Okay.
Okay, so Chris, Nina, Tiarna, and Craig, you should be able to unmute yourselves.
I am unmuted.
Everyone else is muted while we do our lecture and get going.
So, thank you all.
Is there a way to get the four of them on the screen at the same time?
I don't believe so. They should pop up when they start talking.
And you can switch the view to have the person talking being a big picture, as opposed to being a bunch of little pictures.
If you select something called speaker view, which is in the upper right-hand corner, it will make the person who's talking appear larger.
Okay, so as far as, you know, we're going to preserve these as web, YouTube behind a, you know, with password. So this is where we'll start doing that. So if you don't want to be recorded, shut up. So I'm Chris Stavroudis. I developed the modular cleaning program, and I'm thrilled that all this is happening. My drink tonight is starting, well, it's gone now, but it was a dark and stormy. And then I'll be switching to delirium tremens, which is the color theme for our PowerPoints as well. And I have a whole list here that I'm not following. So, Craig, can you do your little, are you up for that?
Sure, I got it here.
Okay, what are you drinking?
I have a banana, strawberry, mango, pineapple, sweet tea, virgin. So that'll keep me busy for a while. Do you want me to do my
do your little shtick.
My PowerPoint?
Perfect.
All right, a lot of what we, one thing that we want to clarify is, let's see if I can share this. Uh-oh, can you see it all?
Yep, it looks good.
A lot of times we talk about conservation science, but there really are two versions of that. Conservation science, and we'll call it conservation with the big C, and that'll be dealing with primarily conservation scientists, and they're the ones who will test materials for us. Like to come to mind, like when cyclododecane came onto the scene. The conservation scientists would then analyze it and make sure it's appropriate for us to be able to use on our materials. And also like carpapole, you know, going through the whole thing about whether carpapole in our gels, how much, you know, if that was appropriate and how much was staying on our surfaces and things like that. So that's conservation scientists. And they're the ones who don't really get into bench work, doing things that are any interventions or any treatments at all. But then we'll go to conservation science with a small c, and that's more for our everyday applications. That'll be our understanding, us practicing conservators, the understanding of the chemical interactions between different things and how they'll work once they've come away, you know, back from the conservation scientists. We use those, but we have to understand how they work as well. So conservation science with the small c, that's us, understanding how they interact with each other, how they're going to blend, how solvents will react with the different resins, and how different solvents, you can have B-72, but different solvents will make it behave in so many different ways. And so that's the conservation science with the small c that we need to understand. And that's really, I think, where most of what we're doing with the MCP is being able to understand conservation science with the small c. Did that make sense?
Yeah, and that differentiates, that's the kind of, between the conservation science for conservators, this is the small c conservation science, the practical conservation science, not the,
Right.
well, I've got some charts and graphs, but.
You always do.
Yeah.
But that's good. All right, so that was just a distinction we wanted to clarify so that we're not confusing the two. So we're doing conservation science with the small c. Okay? I'll stop sharing. And we're back.
So Tiarna?
Sure, hi. My name is Tiarna Doherty, and I'm a paintings conservator. I had the good fortune of collaborating with Chris, I think from 2002, because as Chris introduced his plans for the modular cleaning program, he would send them to me and I would call him with all kinds of questions and sometimes suggestions. And at some point I said, you know, Chris, I think it would be really helpful if we had a workshop. So we started workshops. I had to bail because I left California for the East Coast to become head of a lab at the Smithsonian American Art Museum. So Nina took over running the workshops. But I was so happy that Chris and Nina went online with Zoom because I'm currently working on a PhD in art history, but I miss exercising the side of my brain that deals with chemistry. So I will be a little more active in the chat. I'm so happy to see you all. And that's it for me.
So Nina, oh, Tiarna, what are you drinking?
Oh, okay, so embarrassing. So I had a really good meeting with my advisor and I was so excited to celebrate. I thought we were starting at 5. So I made Nina's drink using the Esquire recipe that someone else was talking about earlier. So I had my dark and stormy. So right now I'm on water.
Very sensible.
Hey everyone, I'm Nina Roth-Wells and I am drinking a dark and stormy, as you know. Yeah, Tiarna texted me at 5. She's like, oops. I'm always challenged because these are listed in Pacific time and I'm always freaked out about starting at the wrong time. But so I took the first MCP workshop in Ohio in 2005, right after I found out I was pregnant with my son, who is now a freshman in high school. So I have been MCPing for a long time. And I was just so thrilled after this workshop because I really clicked with the method and the way that Chris's brain worked around the MCP. And I felt like it was just a wonderful tool to be able to really pinpoint and select cleanings instead of just using what might work. You can actually use what does work perfectly. This spring, when we were all in lockdown, I approached Chris about doing these online workshops, and I thought that maybe 35 people would sign up, and we were very surprised when over 1,000 people from all over the world signed up. And then after doing 4 workshops, we discovered that there was kind of a need for just having some more informal discussions that the workshops just didn't allow for. And Luke and Chris came up with this great idea to do this sort of online happy hour discussion group. So I'm thrilled to be here and I'm thrilled so many of you have come.
So Luke, we know what you're drinking, but.
I'll reintroduce it for anyone who wasn't here. I have a nice paint pear brandy from St. George. So we, like Nina said, started forming this idea because we noticed that a lot of people were having either trouble with scientific fundamentals, or they just had wonderful questions that it really made us think deeply about certain problems. So we thought a really good way to get the community together and get the profession communicating with each other more was by doing something relaxed and informal and kind of fun. So if you're wondering about the title of this, it's Drunk Conservation Science for Conservators. We thought it would be a little bit like Drunk History. If anyone is familiar with that program, we're not going to get that drunk if anyone's face down on the floor, something bad has happened. But so we're planning to do these once a month if we can, and we're hoping to have guest lectures whenever possible. So either conservation scientists, conservators. This is not necessarily about becoming conservation scientists. That's not what we want anyone to do. And we don't even necessarily want to learn everything that conservation scientists do. We want to learn how to apply that information in our daily practice. I, like many of you here, am a bench conservator. While, like everyone else, I also dabble in chemistry, material science, and work in the lab. I'm mainly a bench conservator, but early on I realized how integral the sciences are to my everyday practice in every way, whether it's for my own health and safety, or for the health and safety of the object, or just learning about new and exciting interactions that keep the profession fun and engaging. You know, there's always something new to learn, and that's what's exciting about all of this. So hopefully you can join us once a month for a 30 to 45-minute lecture. Then after the lecture, we're going to have kind of a small panel discussion, almost like this is a conference where Chris, Tiarna, Nina, Craig, and I, and whoever the guest lecturer might be that day, will have a little discussion about applying the principles from the lecture to our daily practice. After that point, we are going to open Pandora's box, and it's going to be a free-for-all Q&A. So during the lecture, if you want, you can send questions about the lecture to the chat, where Tiarna and Nina have graciously volunteered to monitor that and queue questions up so that we can answer them at the end. And after we get through the lecture questions, you can ask basically whatever you want, whether it's MCP related, solubility theory, whatever you want to go into. If we can answer it, we will. So with that, I think we can get into my PowerPoint and get into tonight's lecture. Okay, so I'm going to share my screen. Okay, can everybody see this?
Yes.
Yes.
All right, great. So here are our email addresses if you need to contact with questions or concerns or anything like that. Before we get too far into this, we were going to have a guest lecturer tonight who unfortunately couldn't make it. They were going to talk about the theme of drunk conservation. Obviously, we all know how serious overindulging in alcohol is, so obviously this program isn't about promoting that. It's just supposed to be a fun program for everybody, where you may lightly indulge or not indulge at all. So feel free to do whatever you want. There's no pressure to drink or do anything you don't want to. So we have a surprise topic for the evening that I think is pretty apropos. We're going to dig into the science of ethanol this evening for our first talk in drunk conservation science for conservators. So the ethanol molecule, C2H5OH, here on the top left corner is the ball and stick model, where we have, can you all see my mouse? Is that showing up? Okay, great. So we have a carbon atom here with 3 hydrogens on it. That's a methyl group. We have a carbon atom with 2 hydrogens connected to an oxygen. That's red. And then a hydrogen branching off of that. That's your hydroxyl group. This oxygen is red. It pulls electronegativity away from the carbon as well as this hydrogen. So when we come down to this image below, that is the electrostatic potential map or diagram, which is also sometimes called the van der Waals surface. we're especially concerned with the surface area of molecules when we talk about van der Waals interactions. That's extremely important. So we can actually look at the electrostatic potential around the entire molecule. You'll actually see this hydrogen over here connected to the oxygen, because the oxygen is so electron withdrawing, is actually showing up more positive than the hydrogens attached to these other carbons. So you notice that these are kind of a lighter blue coming over to kind of a green blue over here. And on the right-hand side, we have the ethanol molecule again, rotating around, so you can see it in 3 dimensions. So making sure that we're always thinking about these molecules as real objects that actually exist and not just stick drawings on a piece of paper. So Chris is going to start us off this evening with our first lecture. And so if you have any questions during the lecture, put them in the chat and we'll get back to them later. So Chris, I'm going to stop sharing and turn it over to you.
Okay, I will start sharing. So you already know all this. So ethanol or ethyl alcohol. We know it's a toxic material. It's a signal. This is kind of following on what Luke said, you know, that we didn't want to make this a call for everyone to get falling down drunk. We kind of did a quick look and saw that nearly every museum was having cocktails with curators. So we had to kind of up it a little bit and do something a little bit more than cocktails with for conservation science. So it's the single most important substance of abuse in the US and probably everywhere else. A blood level of above 0.4% can be lethal. This kind of surprised me that 2 grams per kilogram of 200 proof ethanol is the LD50. So were I in that test group, I would like to be on the 50% that lived as opposed to the 50% who died. I'm sure they didn't actually kill 50% of the test group. It was extrapolated from other morbidity research, but still 2 grams per kilogram, that's not a lot of ethanol to drink to be 50% lethal. And as Luke was saying, alcoholism or alcohol use disorder is a really terrible endemic disease and causes all sorts of misery to families, and you know, when it gets into traffic accidents and that sort of thing is just horrible. So in the US, we have a system called proof, which originated in England, but has a slightly different definition. But it's basically 2 times the ABV, the alcohol by volume, which is used in the EU, UK, and I presume elsewhere in the civilized world. So 200 proof is pure ethanol. That is without water, anhydrous absolute alcohol. And that's not to be confused with absolute vodka, which is not 100% ethanol, but do a lot of spending for arty things, so very good. As far as conventional distillation goes, 190 proof or 95% ethanol is the highest alcohol content you can get by distillation. So we'll be talking about that in a little bit. And this is because there's an azeotrope at 95.63% ethanol by weight and 4.37% water by weight. Pure alcohol is sold as 100% or 200 proof. It can also be called absolute alcohol, 200 proof alcohol, and generally a special permit's required to get this in your lab or studio. Although it appears now you can buy it by paying a hefty alcohol tax. So I saw one site where you could buy, I think 500 mils for $70 and have been paying the excise tax on the alcohol and get it that way. 95% alcohol, 190 proof, is also requires a permit or buy it and pay an alcohol tax. But it's also sold in some states in the US as Everclear, which is not lab grade. It is intended for drinking or using in mixes. Hopefully no one tries to drink it straight. So the important thing is to check your safety data sheet and see what's in your ethanol, because poisons may be lurking. Denatured alcohol is what we normally get when we buy lab supplies, getting alcohol, ethyl alcohol, denatured alcohol. And it's made toxic to keep people from drinking it. It kind of hit me that the word denatured implies that drinkable alcohol is natural, and that denatured, the natural, has been taken away by making it toxic. It can also be referred to as methylated spirit. In the UK and other places, I believe it's called IMS, industrial methylated spirit. And usually it's 95% ethanol, 5% water, with the denaturant added. The common denaturing agents are methanol, which is highly toxic, isopropanol, less toxic, often requires a higher percentage, sometimes as much as 15% added to the 95% ethanol, 5% water. Ethyl acetate is often used in cosmetic applications, and there's some really odd stuff thrown in there. I saw one recipe that had jet fuel, another had toluene. So the typical denatured alcohol is 5% methanol. So it comes out to 90.25% ethanol, 5% methanol, and 4.75% water. Methanol, as I hope you all know, is highly toxic. Toxic by ingestion, inhalation, and passes through the skin or eyes. 10 mils ingested can cause blindness, which is fantastically scary, by destruction of the optic nerve. It's a neurotoxin. Surprisingly, its LD50 isn't as high as you would think, but I guess they don't consider going blind to be a lethal dose. And in the US, I don't know if this happened elsewhere, but there were a whole number of hand sanitizers that were banned and cautioned against on the news because they were formulated with alcohol that had been denatured with methanol. There is anhydrous ethanol, which is a special or special form of denatured alcohol, which is made from 100% ethanol with the denaturant in it. So 95% ethanol, 5% methanol. There's one for cosmetics that's 95% ethanol, 5% isopropanol. Again, these are anhydrous, so they'll absorb moisture from the air, but they don't have that typical 5% water in them. So always check the SDS from your supplier from whom you purchase your alcohol. Here, there's some odd ones, 5% methanol, 5% isopropanol. This is all in the 95% ethanol, 5% water. 5% isopropanol, I've already mentioned. Tert-butanol seems to be used fairly frequently, also sometimes for cosmetics at a very low concentration. And the one that struck me as really strange is 95% ethanol with 5% water, 4% methanol, 1% methyl isobutyl ketone, 1% ethyl acetate, 1% hexane, and a splash of toluene just to round off the palette. So let's look at the distillation of ethanol. This is a commercial copper still. You heat the part of it on the left and put water in the part on the right, and the condensing coil is in the cup on the right. So onto the kind of topic, azeotropes is a mixture of solvent that have a lower or higher boiling point than either individual solvent. And we'll be focusing on the ethanol water azeotrope. So if we look at ethanol, it has a boiling point of 78.4. Water, we know, has a boiling point of 100. And the ethanol water azeotrope has a boiling point of 78.2 degrees C. So even that 0.2 of a difference in suppression of the boiling point is incredibly significant. So let's look at a easier to visualize azeotrope. This is the acetone and hexane azeotrope. And I'll be talking about this a little bit more later. Just to want to mention that we should never be using hexane. It's it's metabolized in the liver to be a neurotoxin, and the man who created Nike shoes had been making the rubber soles for his prototype shoes in a waffle maker in his house using hexane as the solvent, and developed neuropathy in his fingers and toes that never went away. Kind of all the king's horses and all the king's men could never get his sense of touch back into his fingers and toes. So avoid hexane, avoid methanol. So here we have the hexane acetone azeotrope, and we see at 100% acetone we have a boiling point of 56.1. 100% hexane, we have a boiling point of 68.7, and that magical azeotrope point, 45.6 hexane, 54.4 acetone, has a boiling point of 49.7. So that's well below either the hexane or acetone by themselves. With ethanol water, it's a little bit more tricky. We have the 100% water boiling at 100, 100% ethanol boiling at 78.4, and that azeotrope is right here at 78.2, and that's 95.63% ethanol, 4.37% water by weight. And here's how the distillation process works. We start with the stuff we're going to distill the, I'm blanking on what it's called. It's not the wort, it's the
Mash.
Thank you, mash. We start with that at 10% alcohol. We heat that up. The 10% goes to vapor concentration at 40%, and this would be the first distillation. So that's why many spirits are at 40% alcohol, 80 proof from that first distillation. We progressively distill or use a fractionating column, and we go back and forth until we get to that 95.6% 95.6% ethanol, 4.4% water. And we can't go above that. That's the azeotrope. That's where the composition of what's being boiled equals what's coming off as steam or as vapor. Those two are equal. So here's a little picture that shows, I may have been okay as a scientist, but I could never be an artist. But here we have a mixture of solvents at the azeotropic concentration. We have it boiling, we have it over our little heat source, and we're at the azeotrope, so we have 95% ethanol, 5% water in the beaker, and we have the vapor coming off at 95% ethanol, 5% water. And this is a true azeotrope. This is where we're at the boiling point. The mixtures of the vapor and the liquid are the same. So one of the things we hope to look at and maybe talk about in a future seminar is these boiling points. These azeotropes are formed at boiling points, but we're working with evaporation at room temperature. So we're making the assumption, and possibly incorrect assumption, that the azeotrope is the same at room temperature as it is at the boiling point of that solvent mixture. But at room temperature, we are assuming that we have our liquid at 95.5% ethanol, 5% water, and our vapor is 95.5% ethanol, 5% water. What happens if we have our liquid at some other concentration? Say we have a 50-50 mixture of water and ethanol. That's what will be in our beaker, but what's evaporating away is still that azeotrope. So we're losing 95% ethanol, 5% water from that 50-50 mixture of water. So that liquid in the beaker will change as the azeotrope evaporates away. So if we start out with 100 mils or 95% ethanol, 5% water, and 10 mils evaporate away, and that what's evaporating away is also the 95% ethanol, 5% water. But what if that's 50-50% ethanol water? So we have our 50-50 ethanol water. We're losing 10 mils in volume, so that will be 10 mils of the 95% ethanol, 5% water. So it'll be 9.5 mils of ethanol, half a mil of water in the vapor. And what are we left with? We're left with 40.5 mils of ethanol and 49.5 mils of water. And we've gone from 50-50 ethanol water to 45% ethanol, 55% water. So what does that mean? That means that as we're using a 50-50 ethanol water mixture, as it evaporates, we're concentrating the water, decreasing the amount of ethanol. And that might be fine, that might be bad. If we're in a situation where we don't want to have water, any more water than we expect to be present, we might want to be quick about swapping out our swabs and not leave them on too long so they don't evaporate and concentrate that water amount. So if we take a mixture of the acetone hexane again, if we start with a 20% hexane, 80% acetone, and lose 10% of that by volume, we end up with 16% hexane and 84% acetone. So what happens is, as it evaporates, it moves away from the azeotrope. So in this case, our acetone will be becoming more and more concentrated as our swab evaporates. That's an advantage of working in as azeotrope, is that what's on your swab as you're cleaning stays the same. If we go to an 80% hexane, 20% acetone, as that evaporates, we will enrich the hexane, decrease the acetone percent. So here we have a system where we're getting progressively weaker in our solvent strength by being on the other side of that azeotrope. So this is has been presented years and years ago by Manchel and Kleiner at IRPA, and Chris Augerson has also talked about this a lot in his publications. And I want to stop screen share. So that's my little spiel for tonight. And now Luke's gonna enlighten us.
Okay, can everybody see this?
Yes.
Okay, great. So before I get into this part, I want to reiterate one thing that Chris said that kind of slips under the radar, but that is foundational to how we think about azeotropes. Azeotropes are determined at their boiling point. We use them at room temperature. So they may not actually exhibit azeotropic behavior at room temperature. And so this is a lot of research that is just starting to come out. I've been hearing rumblings about this in physics journals and things for a few months. I've been looking into this. So when you are working with a reported azeotrope, be very careful with what you're doing, because your mixture may actually be evaporating heterogeneously. It may not be evaporating the way you would think it is. So that's something that we're going to hopefully dig into more in the future. And luckily, Chris is reining me in from digging into this, but there's some very interesting things going on with water and ethanol azeotropes that hopefully we'll get into later. So when we were talking about these, Chris had brought up the 50-50 ethanol water mixture. And we were brainstorming with Chris McGlinchey, and he asked if I had ever heard of protein cracking, which is common in furniture conservation studios, or using a mixture of 50-50 water and ethanol to remove hide glue from joints or from marquetry surfaces. You can do this with rabbit glue as well, or fish glue. It works best with hide glue. So I said, yeah, of course. And so he recommended that I look into this because there hadn't been any literature published on this particular issue. There is a ton of information, of course, on protein chemistry. It's probably the most important scientific development in the last 120 years is research into proteins. But protein films, when they're dried, don't get much attention. So we're going to dig into this. So what would cause proteins to crack as a dried film? If you have proteins inside, say, a mortise and tenon joint in a table or something like that, it's dried, but you need to disassemble it, but the protein is partially frozen. Some of the glue is still actually adhered to the surfaces. Well, you can inject a mixture of 50-50 water and ethanol to loosen the joint and crack the glue. It doesn't actually dissolve the glue, but it causes the glue to break apart into little particles. And sometimes the effect is so severe, you can actually hear it audibly cracking and crinkling. So when we use protein glues, we're all aware that we prepare them by heating them with water. So why isn't water as a solvent working with protein glues later on in their life? So to get into that, you have to look a little bit into what actually forms a protein glue, a little bit of protein chemistry. We are not going to deep dive into protein chemistry. This is just going to give us a basic outline. And even this slide could be controversial with a protein chemist. But when we look at hide glues specifically, and when I say hide glues, I refer to animal glues that come from mainly bovine sources. We're not looking at fish or rabbits. That is mainly composed of 4 amino acids. Those are glycine, alanine, proline, and hydroxyproline. If you look at these, they all have an amphiphilic character. They all have portions that are polar and portions that are not polar. So we have a hydroxy group on this essentially carboxylic acid here, this amino acid, and then this nitrogen is also polar. It has a lone pair of electrons on it. When we go over to alanine and we look at it, it's essentially the same structure with an extra methyl group branching off with a little bit of stereochemistry. We have a chiral center here, which means it's attached to 4 distinct groups, one of them being this nitrogen, which is on a wedge, which means it's coming towards us on the paper. Proline has a paraloid ring, which is basically a 5-member ring where nitrogen replaces one of the carbons here, which is also polar. And then we have the same carboxylic acid group over here that is polar. And then we have this entire section over here, which is nonpolar. And then over here, the hydroxyproline, same thing, except that we have an extra hydroxy group. And then this hydrogen as well is also chiral, or this carbon is chiral, which causes this hydrogen to be pushed back. This OH group is pushed back, which means it has an enantiomer, which means there's another form of it where both of those are on a wedge instead of a dash. So if we all remember back to our Chem 152 days, the enantiomers are like your hands, where they're mirror images of each other, but if you superimpose them, they don't match. That is what the enantiomer is. But so all of these amino acids are amphiphilic, and that's really important to remember as we move on. So when we get into protein chemistry, people tend to freak out and think it's something special, but it's really not. We're actually really familiar with proteins when we start to think of them as polymers. And all these amino acids are just monomers. All of these are just linked end to end in a very similar way as to polymers we commonly deal with as surface coatings. It's a very similar type of linkage or a similar type of reaction. These specifically for proteins and amino acids are peptide bonds, and that's a dehydration reaction between the carboxyl group and the amino group. So I'm going to circle that. So this is the amino group, the NH2. This is our carboxyl group, the C double bond O, OH. What happens is an interaction between the OH and the H from the adjacent amino acid, which produces a peptide bond, which links the two together and then releases a molecule of water. Okay, so a peptide bond is nothing more than a covalent bond. It's just what we call a bond specifically between the carbon and nitrogen of the adjacent amino acids. And then notice here in green, I have this other circle here showing that this OH is also ready to participate in the next linkage. Okay, so when we look at this very short chain over here consisting of just 2 monomers, we have, again, a polar portion here, a non-polar portion here, a polar portion here, a non-polar portion here, and a polar portion here. So it's an amphiphile. It has a dual character. It's hydrophobic and it's hydrophilic. It's water-loving and water-hating. Basically, it doesn't want to be in contact with water. So the way that these form and they self-assemble in water is basically the hydrophobic effect with some other interesting influences. But the hydrogen bonding is the main factor in the shape of the collagen, which is the main composition of these protein glues. It forms what's called an alpha helix structure. That's this structure here. So it's basically 3 long strands, those 3 long polymer strands that are wound together. On the exterior of that, in the aqueous environment, like in a biological system, you have the more polar groups like the hydroxyproline or the proline, and on the interior you have the smaller amino acids. It's more hydrophobic in the core, and that way you can almost think of it as a really complex micelle system, essentially. When you also look at these in a biological system, you have a resonance structure where the OH is deprotonated, and you have different things going on. We're not going to dig into that because we're looking at this as gelatin, which is processed collagen, not collagen that exists in a biological system. So don't mix the two up. So again, the shape of this is the secondary structure of this, which is determined by the hydrogen bonding of all those amino acids, and to a lesser extent, those van der Waals interactions at the center of these strands. And these are intermolecular interactions between the strands. So the peptide chains are built up with chemical bonds, with covalent bonds. It interacts with the other chain through intermolecular bonds, which are hydrogen bonds and van der Waals interactions. Those are not covalent or chemical bonds, which is an important distinction. So that when we do heat these up in water to about 120 to 140 Fahrenheit, we actually cause those strands to uncoil. So it goes from a 3-stranded coil to single coils that are separated in the water, and at that point it's actually technically a colloid, but it's a solution of proteins and water, and that's all it really is. It's nothing more complex than that. You have long polymer chains dissolved in water at that point, similar to any other polymer that you might dissolve in a solvent and then spray onto a canvas or a piece of furniture that'll then reform in a polymeric network. It's very similar to that. There's one exception. Due to the specific structure, these specific amino acids, they have interesting properties. One is that as this cools, it actually can't really go back to that alpha helix structure. As it cools, it lines up kind of like a misaligned zipper. Or if instead of having the zipper lining up like this, it was lining up like this. Okay, and that causes a different type of bonding pattern. It's still hydrogen bonds, but it's not tightly wound in a coil anymore. And this is the gelled state. So if you've ever worked with high glue or protein glues, as they start to cool, it starts to gel. It's not a solid yet. It's not quite a liquid. There's an in-between stage, and that's this cooling stage. Finally, it forms, if we hope, a gelatin, which is pure, essentially collagen for glue, and it's still not coiled, but those all of those polymer chains are linked more strongly by hydrogen bonds and van der Waals interactions. So when we look at these glues as a dried film, which again, there's very little information about. I have a couple papers referenced here that are phenomenal. This one on this slide is excellent. Animal glues review their key properties relevant to conservation. High glues specifically, when we're talking about the bovine-based glues, not necessarily fish or rabbit glues, although it does apply quite a bit to them, they should have about 12 to 14% structural water. That is water that is actually part of the chemical structure of these polymers. As the water content decreases, the molecule becomes less stable. There are different factors that water participates in and stabilizes. Some of them are steric factors, where it just physically takes up space and puts things in certain positions. There are hydrogen bonding interactions and things like that. But as we lose that water through aging, through changes in relative humidity, extreme temperature fluctuations, the film starts to lose water. And we're all pretty aware of this when we see old protein glue films that are cracked and they look like they have almost a craquellar pattern to them. When it gets to about 0.3% water content or less, that glue at that point is practically insoluble. that is almost totally cross-linked and there would be no way to dissolve it. You could swell it and possibly remove it, swell it and separate it from the substrate, but you're not going to dissolve it at that point. And I think that's a concept we're all really comfortable with when we deal with cross-linked coatings. They're quite insoluble and they can usually only be swelled and removed. These cross-links specifically, the mechanism is not totally known yet. There's not, again, a lot of research into this, but it's believed that it's due to esterification and amine formation between polymer chains. So basically you have cross-linking between those chains that we looked at previously that were only hydrogen bonded. Now those links are actually covalently bonded, and they're bonded 10 times more strongly than with the hydrogen bond. So a covalent bond is usually 10 times stronger than a hydrogen bond. That can change depending on, you know, pH and other conditions and things like that. So we can look at this and make a pretty good guess that as a film goes from 12 or 14% structural water and approaches that 0.3% mark where it's totally cross-linked and insoluble, along that gradient, there is some level of cross-linking that occurs because it's not just transitioning from not cross-linked to cross-linked. There's some kind of gradient there where cross-links are forming. So as it's losing water, it's forming cross-links in that dried film. And most of us that have worked with, gilt work or, frames that have protein glue, you'll notice that crackled cross-linked residue on the surface. So as these glues dry initially and then further through the dehydration process, the internal stress of the glue actually increases as the water loss increases. So as dehydration occurs, stress increases. And again, that's what causes that cracking pattern that we see. So we can consider that as cross-linking increases, as dehydration increases, internal stress also increases. The reverse of that is that as hydration increases, as you rehydrate it, it becomes less stressed if you catch it sometime before that 0.3% point. And again, we've all likely seen this in whether it's a synthetic polymer or a natural biomolecule. And so looking at this, so why is any of this important? Why wouldn't water dissolve in aged hide glue? Well, if you put water onto a polymer surface that's cross-linked, it's probably not going to dissolve for a lot of different reasons. If we put water into this film, into this surface that's cross-linked, it's also not going to dissolve due to those cross-links. And why won't ethanol alone work? Because there are portions that are extremely polar and will still be dissolved better through the hydrogen bonding and interactions with water. So you might be able to use ethanol, and if you let it soak for 48 hours or something under heat, you might get full dehydration or denaturation of the protein. But that's not necessarily something we can do with an object, especially a wooden or organic object, where you can't expose it to water and heat for a long time. As we've seen, those amino acids, they consist of portions that are polar and non-polar. But when we look at ethanol, at the beginning we looked at it and showed that there are portions that are polar and non-polar. So it's that same like dissolves like concept that we think about with solubility. We're going to have interactions between the two carbons on the ethanol with the portions of the amino acids that consist of carbons. That's not an interaction that would occur with water. Water does not contain carbon, so you're not going to get van der Waals interactions between the water and the protein structure. It's just not going to occur. The other thing is that, of course, there's also the hydroxyl group on the ethanol that's going to participate in some hydrogen bonding. And it's also going to participate in hydrogen bonding with the water and the solution. So it's actually going to increase wettability of the water. It can actually reduce some of the surface tension and some of the intermolecular cohesion between the water molecules. They kind of spread out a little bit. That can also actually help the solution penetrate into whatever surface or joint or whatever it is you're working with. So another point that we're all generally familiar with is the denaturation of proteins. If we look at an egg that you're cooking on a skillet, well, you're denaturing the protein through heat. But the same reaction can occur with particular organic solvents, and specifically alcohols do a really good job of denaturing proteins. If you could do this experiment now if you wanted. You could take albumin from an egg and put it in a glass and mix it with water, and you'll actually find that you'll have what looks like cooked egg in the glass, and that's the denaturing of the protein. So by bonding to those nonpolar portions of the amino acids, the alcohol is actually acting as a bond disruptor. The protein itself can't interact and bond with the proteins around it in the way it would normally like to, especially if you hit it with water first and it starts to soften a little bit and it's trying to relieve some of that internal stress by hydrating. If you have alcohol in there, it's going to disrupt that interaction. When the amino acids in the hydroxyl group are in the wrong configuration, the chain of that amino acid also becomes unstable. And so how can you mess with the configuration of that chain? Well, dehydrate it with an alcohol. A dehydration reaction will completely remove that, and now you have an entirely unstable protein chain. And so again, the water alone, it's not going to participate in those van der Waals interactions, so you actually have to have this mixture. I'm not quite certain if there's any magic to the 50-50 mixture of water and ethanol. I'm sure other proportions would work. But traditionally, that's something that we've used in the conservation studio. And kind of one of the points of this series, that's something that one of my teachers, William Patrick Edwards, has been using since the 1990s, even though we may not have understood the molecular mechanism, we understood that it works. So we're taking these principles and actually applying them to our practice. So here is a diagram of that, and so I drew this in a program called ChemSketch. So it doesn't look great, but if you'll bear with me, we have two amino acids here that would be that are representatives of amino acids that would be in a dried protein film. We have ethanol molecules, and we have water molecules. These yellow bonds are actually van der Waals interactions between these hydrogens. So that's the van der Waals interactions occurring. These red bonds are hydrogen bonds, and those are occurring between oxygens and hydrogens and nitrogens and hydrogens. So you can see how if you just had water, there are very large portions of this chain that you're not going to be interacting with at all, which impairs the solubility of the entire protein chain. So by combining both of those and bringing them to the surface at the same time, you get a much better solvent effect. So what causes the protein cracking? What actually causes that to crack and not dissolve? Well, so it's not going to dissolve because we already said that it is cross-linked. And one of the ways that you learn about polymer chains in a traditional polymer chemistry class, you think of it as an actual chain of rings interconnected. Well, one of my teachers explained it to me as being, instead of a chain of rings, it's like a chainmail shirt. That's really a cross-linked polymeric network. You have cross-links between chains that weren't there before. You also have links between the polymer strands themselves. So you actually have a system that is very stable and essentially insoluble. So you have those cross-linked portions that are held together strongly by those covalent bonds because some of those hydrogen bonds have been replaced by covalent bonds. And you have regions of the film that are still held together by hydrogen bonding and van der Waals interactions. So you have a mixture of those two. So you essentially have one region that's strongly bonded and one region that's less strongly bonded. And those regions are interspersed throughout the entire film. So we've already looked at the bonding of ethanol and water to that film. So if we start to dissolve those areas that aren't cross-linked, those areas that are available to hydrogen bond and interact through van der Waals interactions, we can start to dissolve those and relieve some of that internal stress that we talked about earlier. And so by relieving that internal stress, the polymer itself, that network, is cracking apart. And so this is not anything that has been published or researched. This is my best guess at this, this mechanism. But by relieving that stress of the cross-linked film through dissolving those more soluble portions of the protein, you can actually cause that cracking to occur. And at least that's my best guess of it. So that's your physical cracking, which if you listen closely, you can actually hear occur. So after all that chemistry, you probably need a drink. So I'm going to stop sharing the screen now.
I have a question. Can you hear me?
Yep, yes, go for it.
This is interesting because I happen to be faced with a problem as it relates to a painting on canvas that's been glued to its stretcher throughout the width of the stretcher. So I'm wondering how long that cracking process takes. Is this something that could potentially be used in my application for releasing the canvas from the stretcher in a timely way so that the hide glue perhaps that's in the canvas isn't affected, or that the paint films aren't blanched? How quickly might that happen, this cracking process? Or is this something you would recommend trying?
I would definitely recommend trying it as a small spot test first to make sure you're not getting any negative reactions. But generally, when I do this, it's in a piece of furniture, so there is a ton of hide glue present. So when there's a lot of hide glue present, where there's some kind of gap filling property that's occurred, that glue has itself shrunk already quite a bit inside of a gap. So the internal stress is higher in a system like that. I would imagine in that system that you're talking about is a thin, nice layer of hide glue. So it may not occur as quickly as in a system like that, but when I do it, it's on the scale of seconds to minutes.
Okay.
It's quite quick. And you can also play with the ratio of ethanol and water, because again, that protein glue is going to have a variable composition. We just looked at glycine and a couple other components. There's a lot of other stuff that goes into hide glues that have been produced, since antiquity. So you can have metals in there that are forming coordination complexes and, divalent bonds and things like that. You can have alcohols that were actually added initially with the glue. You can have urea as modifiers, a lot of different things that'll change that particular chemistry that you might have to play with. But I definitely would say it would be worth a try. If you're worried about absorption into the substrate, I haven't done this, but another thing that you might want to look into is emulsifying that material. So you water and alcohol emulsified with pemulon or something like that. That may be a good way to approach that problem.
Wonderful. Thank you very much.
Yeah, of course.
Let us know if you try it and what happens.
I certainly will. I'm thinking though, an emulsifier might not be practical. There's not too much room. I'm thinking maybe injecting the solution between the back of the canvas and the stretcher, and proceeding as it may or may not crack. But my options are few, so this is well worth a try.
I think it's definitely an option.
Can I intervene with a couple of questions?
Sorry, say that again?
Kevin, is this a Spanish colonial painting, specifically Peruvian?
That's an interesting question. This is a Renaissance Italian painting that had been cut off of its stretcher and turned into a room divider, into a screen.
Well, the reason I ask is because there's a whole class of paintings produced in Spanish colonial America where they traditionally glued the canvas directly to the strainers. So this would be a treatment method that would be applicable to a whole class of artifacts. It's very intriguing. I think too, I just wanted to comment that I think the gelling would be counterproductive because it would slow the infusion of the alcohol solution into the glue layer. So you'd end up with your solution stuck either, well, if you applied it from the painted surface, which would be the quickest way to get it to the glue layer, it's going to stay on the surface and not go down behind the canvas. So,
well, if you think about a crystallized glue, that's a solid. You're only interacting with the surface. Although you would perhaps inject it as a free liquid, it's not going to penetrate through that system, that actual crystalline structure that quickly. So you actually are only interacting with the surface. So you could suspend that. And I'm not glued to the idea of using an emulsifier. But by injecting as a free liquid, you may get other interactions, of that material absorbing into the substrate that you may not want. So you're in it because you are dissolving this, from the top down. It's not just going to penetrate through it all, immediately.
But
my point was that the gel is going to keep the alcohol solution on the painted surface, whereas if you introduce it to the painted surface as a liquid, it'll penetrate into the canvas and disappear pretty quickly into the substrate where the glue layer resides.
There's a miscommunication where one of you is saying gel and the other is saying emulsion. So the emulsion doesn't have to be a gel. But what I was going to add was that we know in paintings conservation that a 50-50 water alcohol mixture really keeps the canvas from shrinking. So if you're going to apply a water system to a canvas, a 50-50 water alcohol system is fabulous. It just doesn't cause shrinkage of the canvas.
Wonderful.
Luke, in the chat, some of us have started talking about paintings conservation treatment where, when you're removing one canvas from another that was attached with like a hide glue or a glue paste, we often will use like a synthetic clay to suspend our water in so we can slowly kind of swell that glue and scrape it off. And, in part, really it's to kind of control moisture exposure. So Michael was asking here, maybe if we would think about adding ethanol, but I was also thinking maybe the solubility parameters, like the clay may have an impact on the van der Waals forces. I don't know. I think we've all been thinking that as we suspend the water in the clay, we're just doing that, suspending the water, and the water alone is swelling the glue. So I'm wondering two things, like maybe what about that clay, and then what about adding ethanol? Any thoughts? Or maybe someone else here has experimented with adding ethanol. And someone's saying, Michael's asking about, I think, methylcellulose, that's also used.
Yeah, I think I would probably go the methylcellulose route first. But also, since I'm not a paintings conservator and I may not be working with that, is it like a kaolin type product or is it something else? Because it can also depend on the specific charge of the particle. If it might have a dual character to it. It might be positively charged or negatively charged. So that's something to consider. So I'm not quite sure. Chris, you might have a better idea of this, but I would probably lean towards methylcellulose first if I were to try something like that.
I got nothing.
I know like a lot of people have used laponite. I was just reaching out to someone because I forgot. Yep, laponite RD, thanks to which is described as like a synthetic colloidal clay, but I'd have to look up more information.
I've got a lot of it that I've never used because I didn't like its properties. I'll send you some if you want.
In the post, Philippe just put in the post that the laponite has a very high pH, like 9.8, so that might be something to consider as well.
I've successfully used agarose gel to remove hide glue on furniture, but I've never tried to I've only used it with water, and usually actually slightly warm. So I don't know if there would be a good way. Obviously, if you were to heat it and then try to add alcohol, you'd just be evaporating all the alcohol off. So, but it definitely works well.
Yeah, I mean, a lot of hide glues are definitely, soluble in water for quite a long time. It just depends on what the conditions are, what is conditions of aging, or what the relative humidity is, how much it's dehydrated, what other properties does that particular film have. So it's not like, this system would be the be all and end all of dissolving, hide glue. But if you had an aged hide glue that wasn't first responding to water or warm water, then this would be where you might want to go next, because sometimes you might inject water into a joint and nothing occurs, especially if you work with furniture, sometimes you'll wet something, let it sit for 15 minutes, and the glue just doesn't soften. So it's something that's maybe a next step.
I'll just as an aside, because I do furniture as well, and I've always used vinegar to break open hide glue. And you can warm it, and it helps a little bit, not hot, but warm it. And also it'll go into methylcellulose rather easily and make a gel, you know, as thick as you want. But just as a thought, but I also find that if I have like a polyvinyl acetate kind of, you know, carpenter's glue on a piece of wood, that it'll soften the vinegar when it's gelled. You can set it on it, it'll soften that glue up real nice. The only thing about the ethanol mixture on furniture is that so many of our coatings are so alcohol sensitive that I'm reluctant to apply, you know, inject it into a joint and have it run out. So the worst with the vinegar that I get is that I'll get a clean spot.
Luke, can I ask a question? This might be a silly question. As you were saying that the, oh wait, hold on, am I muted? No, I'm not muted, sorry. You were saying that the hide glue obviously is extremely conditional based on, particularly with furniture, based on sort of what the object had been through and how long, you know, what it had been exposed to. But in your experience, what's the oldest a hide glue is before it becomes resistant? I'm not articulate right now. Before it becomes resistant to warm water.
No, I get what you're saying. And there have been studies on that. And again, it's one of those things that is extremely conditional. So the published papers would talk about, you know, dramatic, for example, temperature fluctuation. However, if something is kept under a particular amount of pressure, it may not affect the dehydration of the glue. So it depends. However, they did, in that paper I'm referring to, which I can put in the link or something, or in the chat, it's referenced in that paper I talked about in the PowerPoint. But they said generally with fluctuating RH and temperature, 30 to 50 years is a pretty good range. If you just want to ballpark something, that's probably something to look at. Again, it's so highly dependent on condition and the specific aging process it underwent. And, you know, its storage currently, if it's had a chance to be an appropriate temperature and humidity and hydrate a little bit, that may have an effect. Is it a museum piece that's been in museum storage with no light and proper temperature control, or has it been in a barn for 100 years? You know, it really just depends. And I think, you know, for me, coming from private practice, I had, you know, wonderful teachers in conservation, Patrick Edwards and Patrice Lejeune, and the stuff that comes into their studio will literally come out of a barn. And, you know, if you try to attack something like that with just water, it's simply not going to work. So it's something where, just like with the MCP, you're doing trials. It's not like you're just moving to this first. Test regular water first, and then move to this if that's not working, you know. And then from there, you can kind of determine what's going on with your coating. Then you might be able to say, okay, well, there's more cross-linking in this film because it's not dissolving in water. And then you can go from there.
Thank you so much.
Yeah.
So there were a couple questions in the chat that related back to the section that Chris presented. And one of them was just, Chris presented some different types of ethanol, anhydrous and different lab grades. And in terms of treatment, is there sort of different uses for the different types of ethanol? Then I have another question about Everclear. So,
I think there are minor differences. The water content is probably the biggest thing. I know for, I'm trying to remember, was it for one of the, there was a polymer that went into alcohol, and if there was too much isopropyl in a denatured alcohol, it wouldn't go into solution. I'm forgetting what that was.
B-72 is very sensitive to the denaturing formula of alcohol if you want to use B-72 in ethanol. And I'm sorry I didn't prepare for this, but there's one denaturing formula. It's a histological denaturing formula. I think it's called Formula 19A, and you can buy it from Humco in the United States, except under COVID. You can't buy alcohol anywhere anymore. And it actually produces a perfectly clear solution of B-72, which I haven't found another denaturing formula that does that. So I want to share that as one practical application of this little session this evening.
I was thinking of, I think Butevar is also sensitive to
yeah.
Water concentration and the denaturing.
I imagine a lot of the acrylics maybe, yeah.
And then there was a question about Everclear. Is it not considered lab grade because there's something else in it besides water and ethanol, or don't we know?
I don't know. It always smells very sugary to me. That's kind of a weird thing to say, but it smells different than alcohol I usually sniff. The brown paper bag.
Can I say something about that too?
Go ahead.
You can detect the source of the grain from which the alcohol is made by the odor that comes over with the alcohol. So there are specialty companies, especially in California, it turns out, that distill alcohol from all manner. So you can specify the alcohol, whether you want it from grapes or corn or rice. So all of that has an effect on the final product. It's very subtle, but as Chris has said, you can actually smell it. And I don't know whether that has to do with flavonoids and terpenes and stuff that are in the starting material that comes over with the alcohol.
Yeah,
But,
that's why alcohol is a universal solvent, and that's
exactly
why we called it spirits, because it took on the spirit of what you
cool.
decanted it from, or what you mixed it with when you're brewing things. But that's why it's a spirit. It took on the spirit, and that's why it's used in perfumes. It's an excellent solvent for a lot of different types of fatty acids and flavones and flavonoids and all that kind of stuff too.
We had another question much earlier from Julie asking if alcohol interferes with pH measurement.
That's an interesting question. It basically changes the pH scale. So it changes,
it's a source of hydrogen.
well, it hydrogen bonds with the water and changes the in the equation for the interaction with water molecules with each other, there is a dielectric constant, and the dielectric constant is altered by the addition of alcohol. So that changes the pKs and all those numbers. So the actual pH scale will change from 14 to 12 to 10 because the amount of dissociation of the OH groups or the dissociation of the water into OH and H groups, the amount of that changes. So while pure water is 1 times 10 to the minus 14, as you add alcohol, the amount goes down and down and down. So your pH range goes from 0 to 14 to 0 to 12 to 0 to 10. So that's one of the effects of alcohol on pH.
Chris, can you acidify alcohol? Alkalize it?
I'm not sure what you're asking. You can certainly dissolve bases in it if you want to alkalize it.
I was just thinking about modifying its behavioral activity in the studio. Would adding a little bit of acetic acid or ammonia, how would that theoretically affect the behavior of the alcohol?
I don't know how to answer that.
Sorry for asking.
I mean, I certainly, alcohol and ammonia do amazing things, probably to the detriment of a paint film. But no, I don't have a salient answer for you.
There is that old Italian paint stripper, alcohol, aqua, and ammonia.
And acetone. You have to add acetone to it as well.
There's a question about denaturing agents and which do people consider to be the safest, relatively speaking?
I would say that would be isopropanol, and have the least effect on solubility. They do make denatured alcohol with ethyl acetate as the denaturing for cosmetics, but I suspect that probably fiddles with the solubility parameter of the alcohol a little bit more strongly than just 5 or 10% of isopropyl alcohol. But as the most common one, if you look at the SDSs or the on the website for the different manufacturers, suppliers, almost everything is methanol.
Chris, we had another question, and honestly, I might have to ask Michelle Gallinger to ask it if she's still with us. The question was, so how much time at room temperature do you expect there to be the evaporation rate? So I don't quite get it. I think it's related to azeotropes, working with azeotropes. I remember you talked about time with the swab, but I'm thinking people are thinking about maybe keeping containers open here or something.
I think it related to the room temperature versus the boiling point evaporations as well, because that's when it was asked during the.
Well, I think one takeaway is don't have open cups of solvent mixtures because they may be changing formulations. You know, keep something over it to keep it from evaporating. I was a little surprised at when I did the calculations to show how the composition changed with evaporation. It wasn't as dramatic as I was thinking. So, but I think when you put it out on a thin layer, you know, you're working with a swab and you put it on a surface, you're getting a lot of evaporation. So I think, you know, in that moment, you're going from swab to surface, you're seeing a lot of change. And I think we see that operationally when, you know, the first roll of a swab, you get a different interaction than as that, you know, you roll a second and third time. I mean, there are lots of reasons for that, but one can be that, you know, you're having evaporation, differential evaporation on the swab on the surface as you're working, and the composition of what's on the swab is changing as you're going.
So I think Chris knows, and Luke and Nina, that one of my favorite things about ethanol, given it's the theme here, was that I learned through Chris and the MCP, just that ethanol has, you know, a hydrophile lipophile balance number, and it has this like surfactant kind of property that we all empirically knew about, but it was so interesting to have a number put to that. I don't know if Chris, you want to say anything else about where that fits into when you're presenting on the MCP. I'm a bit rusty on the slides and where that was, but to me, that was always something really interesting about ethanol.
Yeah, I mean, the fact that we know it reduces surface tension is because it's a surface active agent, just like surfactants. So it goes to the surface of the water, breaks that surface tension of the water. It's a surprisingly, it's got an HLB of, as I recall, 8.1. So it's not as low a HLB as one would think. But I think the story you're talking about was when cleaning acrylic paints, some of the early research that Bronwyn Ormsby did was asking people what they used to clean acrylic paints. And a few people replied that they used alcohol water mixture, 10%, either 1% or 10% ethanol in the water, and that they found that worked better on cleaning acrylics. And Richard Wolbers said, oh, well, that makes sense, because as you're putting water on the surface of the acrylic, you're bringing up the surfactants that are in the acrylic not naturally, but from the formulation. And those are high HLB surfactants, very aggressive surfactants. The alcohol is working as a low HLB surfactant, and the combination of the two reduce the effective HLB of the surfactant. So you're basically, by using that alcohol in the alcohol water system to clean a acrylic, you're minimizing the strength of the surfactants that are coming out of that surface by virtue of the alcohol being present as a low HLB surfactant. And then the funny part of that story was Richard sort of spouted this out at one of the early planning meetings for the cleaning acrylic paint surfaces, the CAPS meetings. I think you were there, Tiarna, too. And the next meeting we had, I mentioned this, and Richard said, "That's really clever. Where did you come up with that?" And it's like, "You said it at the last meeting, Richard." He wasn't even paying enough attention to have it register. It just popped out of his head. So.
Chris, I have a question for you. I am an archaeological conservator, not a paintings conservator. And you said something about the 50% ethanol with water does not swell your canvas. Or
it minimizes swelling of the cellulose fiber, yeah.
So that was my question, is what is the canvas made of? Is it cotton? Is it cellulose? Would it be the same if it was like a linen canvas or a linen?
It's for linen. Yeah, it
is linen
material.
Okay, just curious. Thank you.
To bring it back to alcohol as a surfactant, because that's one of my absolute favorite topics. So ethanol itself, because the polar tail of it is only 2 carbons long, it's not long enough to actually act as a surfactant that will form a micelle, although it's just the right length to reduce surface tension. Because when we think about water, water is hydrogen bonding with itself, and that, again, a hydrogen bond is 1/10 the strength of a covalent bond. It's a strong it's a strong interaction. When you introduce the ethanol to the system, and the famous example that most of us learn about is if you have 50 milliliters of water and 50 milliliters of water and you add them in the same container, you have 100 milliliters of water. If you have 50 milliliters of water and 50 milliliters of ethanol and you pour them in the same container, you have 97 milliliters of solution. So how is that? One of them is that because the ethanol molecules fit in between water molecules. The other thing is that you're breaking up the hydrogen bonds within the water molecules, so you reduce the surface tension. And we all see this when we're wetting something onto a surface with water and ethanol. So essentially, instead of having only hydrogen bonds in that system, you have hydrogen bonds, but you also have the nonpolar, the tiny little tadpole nonpolar tails of the ethanol hanging out in there that are interfering with hydrogen bonds between the water molecules. So you drop that. So that's why it's acting to reduce that surface tension. And then you get longer chain alcohols, which do work as surfactants. So things like sterol, or you'll hear it's sterile alcohol. If you go and look at your shampoo or conditioner bottle and look on the back, it'll probably have that in there. Well, that's just an alcohol with a long fatty tail on it that acts as a surfactant and it forms a micelle in water.
Can I ask Luke a question about having ever tried something like protease to attack or dissolve the animal glue?
I've never found that necessary. I haven't found I've never come up against a high glue that I couldn't remove with either just water and ethanol. I don't see why that wouldn't work, although I do tend to kind of stay away from enzymes. Because I think overall in conservation field-wide, I think that the way we think enzymes work is not really how they work in a lot of those solutions, especially because we're missing the coenzymes in solution, and those are extraordinarily expensive to actually make those fully active. So I tend to just kind of stay away from them, and that includes things like lipase for linseed oil. You don't have the coenzyme for that. You don't have co-lipase for it. And it tends to not open, again, because when we're talking about enzymes, we're talking about proteins, we're not opening, terminal flaps that are exposing active areas and things like that. So I've never really found it necessary. I'm not opposed to it or anything. But I've never come across high glue that I couldn't get rid of with water or ethanol and water. And sometimes a really nice sharp chisel, that'll do it too.
Not so popular with painting conservators.
Well, maybe your chisel isn't sharp enough. I'll send you a Lee Nielsen one.
I'm not sure, I forget what we thought for the meeting on time, but I just wanted to suggest, while we still have just over 100 people, that people just drop ideas in the chat for topics that interest you for the future, and I'll take note of them before you go if you want. Just drop something in the chat. And
Yeah, so this Q&A was really free for all. It doesn't have to be about ethanol. And for future topics too, one of the things we're thinking about that if you want to weigh in on, feel free. We're thinking of going through cleaning painted surfaces, aqueous methods, one chapter at a time, or one chapter every couple months or something like that. So starting with pH and kind of working through that, and then you'll have some homework before that month's meeting. So if that's something that you all might be interested in, just let us know, because it's kind of us responding to what people want.
Luke, you said you have never resorted to enzymes to remove linseed oil.
Mm-hmm.
What's your trick?
Oh, I've got a good trick. I've got a really good trick.
Go to the Facebook page.
So this is something I've been playing around with a lot. So when you start to read a lot of the papers, you'll find that when they start to dig into actual, real scientific studies looking into lipase, when you don't have co-lipase present, often people are using formulations that they find in papers and things like that, and they're often combined with surfactants or high pH solutions and things like that. They find that if you take that solution, remove the enzyme, it has almost the same efficacy as with the enzyme. And here we go. So I spent a long time working out the actual chemical mechanism of how lipase attacks a linseed oil. And what I found is that there are two issues generally with those. One, they generally are worked out in the literature as working inside of biological systems. So the oil is already in an aqueous environment, and it's a free globule, which is how lipase best attacks linseed oils and things like that. It's not a dry film. Or if you're looking at, removing, if you have enzymes for proteins and things like that, they're not necessarily based on dried films. They're based on biological environments where things will also have different charges on them due to the aqueous environment that it's within. So when you have something like a lipase enzyme and linseed oil, you have to have the co-lipase to open up what's called the C-terminal flap. It looks like a little hat. Flips up. So it's that same hydrogen bonding mechanism. It exposes something called an oxyanion hole, which is basically an area of electronegativity within the lipase enzyme itself. So you not only have the catalytic triad of the enzyme, the lipase enzyme, that's going to work to actually break apart the linseed oil, you actually also have that oxyanion hole where the linseed oil will actually stick inside of it, and it actually holds it and makes it stable and stabilizes the oxygen as you kick a double bond up to it and start to pull it apart. So without having that co-lipase, you don't open that C-terminal flap. You don't expose that oxyanion hole. So that lipase is not going to be dissolved well at all by the catalytic triad, because it's not going to kick a double bond up to an oxygen that's going to then facilitate the rest of the chain reaction. So when you look at these recipes that you find, and especially I think the Shelburne Museum mentioned this in Australia, I believe, that they had basically the same results of just using surfactants and a pH of 8.5 or 9 or something like that, and maybe a chelating agent as they did with the same system plus lipase. Lots of benefits to not using lipase too. It's not super expensive. If you want to get coenzymes, they're extraordinarily expensive. Co-lipase is about $300 for 5 micrograms. So it's probably not a cost-effective system anyways in your studio. So that's why I tend to stay away from enzymes. They're a lot more complex than we tend to give them credit for, and I'm not sure we totally understand how they work with dried films and dried materials, as opposed to it within biological systems where they're generally reported in.
Luke, can I just rephrase my question? I was hoping you had a magic trick up your sleeve the alcohol water solution equivalent that's applicable to linseed oil?
Okay, yes, I do. So that is going to be a Pemulin TR2 emulsion. So you're going to start with an aqueous phase. That's going to be pH 8.5 with lysine and sodium hydroxide. You can add citric acid or EDTA as a chelator at a 0.05 molarity, the same with lysine, 0.05 molarity. If you build this in the MCP, it's all at 0.05 molarity. From there, you add your surfactant. For this, I like to use sulfonic JL80X because it only takes about 3 drops of it in 100 milliliters of solution to get to 10 times the CMC, the critical micelle concentration. If you use EcoSurf, you're up to like something like half a milliliter or a full milliliter, something like that. From there, you have your aqueous solution prepared.
Wait, one sec. Where did Steven go? Like, this is awesome. And he just disappeared. Hold on. Maybe he's getting his notepad. There we go.
I'm listening. My cat wanted to go out.
Oh, I understand cat problems.
So this is something that we could also post a summary of on the Facebook page after the meeting. So don't feel like you write it down, but don't go crazy. And
do this. Can you all see my screen?
Yeah, and I was going to say everything that you can do that Luke's going to talk about is in the MCP.
All right, so we're going to begin a cleaning test. This is in my dream sometime. I cosplays. It's like, what is it like to be Chris Stavroudis?
It's a very sad life.
I don't know. Yesterday you said you were on the beach in Malibu while I was dehydrating on top of a mortuary chapel in the desert. So, okay, so we'll start with an aqueous test. So we have our aqueous solution selected here. We are going to remove linseed. We're actually going to remove, we'll take it one step further. We'll remove boiled linseed oil, which has generally cobalt or manganese dryers in it, which form coordination complexes between the oil. So that acts to cross-link it, and actually is far more difficult to remove as opposed to stand oil or even just natural linseed oil. So we can go in here, we're going to remove that from something like wood, my expertise. We'll start a cleaning test. We're going to click yes, but modify. Okay, so we're going to go up to a pH of 8.5, lysine with sodium hydroxide. We are going to add a chelator. I tend to stick with citric acid. I actually really like citric acid for most applications as opposed to EDTA. Something that I would maybe like to write a paper on is the chelating effect of citric acid, because actually it's free form of having three teeth that can bond with something. I think might be able to actually pull things from a surface more easily than EDTA, but that's a totally different topic, but it's something interesting to keep in the back of your head. So we're going to add citric acid. We're going to modify it by adding a surfactant, and I like to use sulfonic JL80X because it only takes 3 drops to get to the critical micelle concentration. And I'm not actually looking to form a microemulsion or anything here. I just want the actual surfactant's cleaning power. When you read the literature on Pemulin TR2, they will tell you that you cannot use it with a surfactant, and it's completely untrue. It actually works phenomenally well with the surfactant. I think actually improves its efficacy. So we're going to modify this, and this is the new MCP version where we can make emulsions. And I'm going to make an emulsion with Pemulin TR2, and then I'm going to do this with Gamsol. You can also use Shell Sol D38. That works really nicely. Anywhere from 20 to 40%. I almost always start with 20%. It seems to work better for most boiled linseed oil coatings. So that is literally the entire system. We have 8.5 pH lysine, 8.5 pH citric acid, sulfonic JL80X, Pemulin TR2, and we have Gamsol. What doesn't show up on this screen is that the Pemulin TR2 is neutralized with triethanolamine, which is T. That is really interesting. It has a nitrogen with 3 ethanols branching off. I can't believe we missed that in our talk. We should have talked about triethanolamine. But so it has 3 ethanols branching off of that central nitrogen with a lone pair, which gives it an alcohol solvency effect. So without adding alcohol to the system, we're getting an alcohol effect. So I actually use this to remove even mixtures of boiled linseed oil and shellac, so layers on top of each other, so you actually get a really interesting solvency effect. The Pemulin TR2 also has a bit of a chelating effect to it as well. So you actually get extra chelating properties from the Pemulin as well as the triethanolamine. So you click yes clean, it has a strong effect with no effect on the wood. And then you clear it always. We're going to use pH 8.5 water. We'll continue with the testing. If we make 100 mils, we're going to make Stevens linseed oil remover. You can type whatever you want in there. And you click recipe, and this gives you your mixing instructions here. So it's everything we talked about, the bicene, citric acid, sulfonic, the triethylamine, the Pemulin, and then it gives you mixing instructions. The only thing that I like to do differently is that when I get to this point, when you're ready to prepare your Pemulin, I actually put the Pemulin in a separate container, and then I take a separate container of the solvent, and then I sift the Pemulin into the container with the solvent. In this case, it's Gamsol, so it's totally aliphatic. It doesn't have any proton that it's going to donate to the Pemulin that would start to gel it. So actually, you form a colloidal dispersion of the Pemulin inside the Gamsol or the Shell Sol D38, which means that you don't get clumps in your final mixture. It disperses really nicely in your aliphatic solvent. So once I add that in there, I then have my aqueous solution in one container, my solvent with the Pemulin suspended in another container. I pour that in, and then I actually mix it with a hand mixer like you use in the kitchen for baking. So it has, you know, just 2 beaters on it, or 1 beater if I'm doing it in a small container. And so that kind of takes the place of an overhead high torque mixer in a really cost-effective way. And so doing that gives you a really nice homogeneous mixture, which does a couple of things. One, overnight your pH doesn't drop because your Pemulin is completely reacted with the surrounding solution. It's unfurled and uncoiled. And 2, you don't have clumps of the Pemulin that have kind of congealed around each other. They're totally mixed in, so you don't have a weird clumpy mixture. So everything is nice and homogeneous, which also makes the pH more stable. So that's the entire thing. That's my special mixture for removing boiled linseed oils. And this works on boiled linseed oil of essentially any age. And we work with that at a pH of 8.5 because a pH 8.5 to 9 is around the point where oils begin to saponify. So we actually start to break down the ester linkage between the glycogen. I've had too much of this brandy to remember, but you start to break down the ester linkages within the oil at that pH. And so it works really nicely for that. It's an extraordinarily complex chemical suite of chemical reactions that occur that we could talk about for hours, but it's a really interesting system for moving boiled linseed oil. So that's the whole thing. And
I want to add that you check the pH with the indicator dye.
Right, so I take about a teaspoon of the emulsion from my mixture. I put it into one of the little MCP mixing cups, and I put 3 drops of the dye indicator in it, and I mix that with just one of those little drink mixers to mix it really nicely. And then if the pH is off, I adjust it by adding either citric acid or sodium hydroxide as a solid, not as a liquid. And so what I'll do, if I'm at a pH of 9.5 and I need to get to pH 8.5, I'll add 10% of my original citric acid content. So if I had 1 gram of citric acid that I started with, I would add 0.1 gram to adjust it from 9.5 to 8.5, or so you're somewhere around there. And the same thing with sodium hydroxide, just going the other way. So that's the special mixture for linseed.
So I have to say that you just covered one of the request topics just like that, which was about removing aged linseed oil. And I also wanted to say that if you visit the MCP in Practice Facebook page, there is a great video of Luke making this actual Pemulin that he just described. And it's really helpful to see sort of how he does it and what it should look like. So when you're doing it, if you've never worked with Pemulin before, you know you're doing it the right way.
Mm-hmm. Yeah, and Pemulin is really not as difficult as people make it out to be. I've actually banished xanthan gum from my studio. I don't use xanthan gum for anything at this point. So I'm all Pemulant all the way right now. But really, if you have proper mixing by using that hand mixer, you have no issues with forming a nice emulsion with Pemulant. Pretty much all every emulsion that I've seen that has issues with forming a nice creamy emulsion is because there wasn't adequate mixing. Or someone did something insane, you know, like added 80% of your solvent phase or something like that.
The trick to using Pemulant is the pH indicator dye.
Yeah.
Without that, you're completely lost trying to measure the pH. Or the pH probe for the aqueous systems, but for the emulsions, you really have to use the indicator dye. Yeah. And fortunately, it's available very inexpensively on Amazon. They sell it for crazy people to measure the pH of urine and saliva.
And dark and stormies.
And dark and stormies. So I think you can get 3 little bottles for $10, so it's not a big deal.
Mm-hmm.
Thanks very much, Luke. I'm going to have to go and watch the Facebook page now. After all these years, I'll have to join Facebook just to watch you make this formula.
Zuckerberg thanks you, Stephen.
There have been some requests to put that video on the YouTube channel where we're going to post this recording, and we'll see if we can make that happen. It's up to Luke.
The private videos are just kind of islands. They're on their own. They're a private video. I'll look in to see if there's a way to form like a private list or a private channel that I could put it in, but it's just available publicly on my regular YouTube channel that I just put in the chat there.
Okay.
I'll do my best to do that though, and I'll see if I can upload it to Facebook as well.
Well, you could just subscribe to Luke's YouTube channel, which I didn't know existed, but now we should all do that.
Yes.
If you didn't know this already, Luke is a bundle of energy. I don't think he ever sleeps, because I will go to sleep and there'll be a Facebook message from Luke, and I'll wake up in the morning and there'll be 10 more about the things he's doing and ideas he has. So he's a treasure to the field. We should be very thankful that he's willing to help us out.
That was supposed to be private. That was just supposed to be between us, Nina.
Okay, I'm sorry.
Well, but it's so great to see, like, Luke, how you've embraced like Chris's work and you're just like running with it. It's really exciting for all of us.
Well, I think it's the same thing as a lot of people. Once they take the workshop, you kind of have isolated areas of knowledge. And I feel like the MCP kind of bridges all of those together. And once you do that, you can kind of, it's like the Keanu Reeves whoa moment where you're just like, wow, I can see everything occurring at once, and I get it now. You know, and so that's what makes me excited about the MCP. That's why I made the Apostle Paul preaching to the preaching the ideology of the MCP.
Isn't Luke supposed to be the one who writes everything down?
Well, there we go.
So there have been some great requests in the chat for future topics. I've written some down. I'm sure Tiarna's written them down. We'll bring them to the, oh, hi, Bluma. We'll bring them to the powers that be and and they'll be in future sessions.
Mm-hmm.
If you have a chance, let us know what you thought about this. If it was,
Isn't he beautiful?
What a cutie. Oh, I'm jealous.
Gorgeous animal.
Oh, sweet. It's time for a treat.
That's what she wants, yeah.
Yeah, it's time for a treat. Origin. Origin treats are incredible.
So feedback would be great.
We've gotten a lot of love in the chat. So,
okay, good.
Yeah.
One of the things too that I think is just worth mentioning at the end about azeotropes is first echoing again that key point that Chris made about the fact that these are measured at boiling point. They don't necessarily reflect what's occurring at room temperature. The second thing with ethanol and water is that depending on your sources and depending on how you analyze the mixture, the azeotrope might actually be in reality closer to 9:1 and not 95 to 5. And there's some interesting research coming out about that. And hydrogen bonding itself, I think we're actually kind of on the cusp of reimagining solubility theory and azeotropes. And one of the things about hydrogen bonding, especially when you look at the electrostatic potential maps, that starts to immediately click, is that there has been some really interesting imaging done on water and ethanol mixes in the 9:1 mixture. And what actually occurs there is not necessarily hydrogen bonding from the hydroxyl group on the ethanol. It's actually occurring from the alpha carbon on the ethanol, from those hydrogens, because that hydrogen from the alcohol is actually pointed slightly, depending on the orientation, towards those two hydrogens from the alpha carbon, and alpha carbon meaning just the carbon adjacent to the functional group, and the functional group is the hydroxyl group in this situation. So the hydrogen bond is actually occurring with that particular hydrogen more so than even the oxygen's hydrogen. And that was released from a physics paper in Japan recently, and I think it's going to kind of make waves pretty soon here, but it's kind of reimagining hydrogen bonding. So just something to keep in mind, and another feather in the cap to Chris for making sure to tell you to actually test these mixtures first and look at what's happening empirically and qualitatively and what's occurring in your studio and on the surface of whatever you're working on. And don't just go by what the literature is telling you is correct. So make sure to keep an eye on those things. That's the end of my sermon to the Athenians. Very good.
Here's one word of advice that I can offer is that I use Everclear. I buy it at the liquor store because it's quick and easy for me. And I buy it by the case. I make my French polish with it. But the word of advice is to wait till afternoon to buy it, and don't wait at the door for them to open to buy a case of Everclear because the murmurs and the odd looks tend to go down afternoon.
Speaking of Everclear, I think, Chris, you mentioned that it varies. It turns out that in the state of California, Everclear is only licensed to be, I think it's 150 proof, maybe even less.
190 proof in California.
Pardon?
You can't get the 190 proof in California.
No, that's what I was saying.
Yeah.
That's what sorry.
I'm actually going through the process right now of applying for a license, and it's available at 190 with licensing, but anyone can buy it at 189. So
Is it 180? I thought it was even lower than that. I thought it was only about 154 or something like that.
If somebody wants to actually build a still.
Well, so that brings up a whole nother thing. Yeah, we should all get rotovaps, and we should be recovering our solvents from our swabs for economic and environmental reasons, but that's a whole nother matter.
Well, it may not even be a whole other matter. That's why you add ethanol to your gasoline. It cleans your engine with the water produced through combustion. So there's another solvent mixture with amphiphilic properties working inside your engine. So it's related to greenhouse gases.
Okay, I think I've had enough to drink. I think maybe we'll call this first session to an end. Can we archive the comments on the side, or do they go away when we say goodbye?
I can save the chat, and then I can actually make that available as a text file wherever we decide.
Oh, fantastic. Okay, perfect.
Mm-hmm. There was one last question that someone sent through asking if other ratios of ethanol and water work for cracking proteins. It hasn't been tested in the sense that a scientific experiment hasn't been set up and then reported on. I'm sure people do this all the time in their studios, whether in the US or elsewhere. So you can just play with it yourself and see. Maybe try the 9:1 mixture. You'll have good luck with that.
Okay.
Thank you all.
Good night, all.
Good night. Those of us on the East Coast are tired.
Thank you, guys.
Good night.
Thanks, Chris. Thanks, everybody.
Thank you,
Bye.
everyone.
Everyone.
All right.
Bye-bye.
Bye.